Okay, welcome back. We will continue today laser diagnostics for combustion research after we have discussed yesterday mainly the reactors with focus on shock tubes and RCM. Today we will focus more on laser diagnostics itself, so application of laser methods to examine combustion processes. Of course, we have only 2 hours for this topic, so we will not go into all the spectroscopical details. Here we have to reference to fundamental lectures from other areas, but I would like to explain you at least different methods which can be used to examine specific details in a combustion or an ignition process. The advantage of laser diagnostics is, of course, we do not disturb our probe volume. If you use a temperature sensor, for example, and put it in the flow, of course, there's always an interaction with the system. If we use optical methods, we have then the advantage not to disturb the process. However, we need optical access, otherwise we cannot examine it. So we have to, of course, we have really different levels to consider. We can apply these techniques for complex gas turbines or combustion engines with some limitations, but more often, of course, we perform these measurements on lab scale experiments. We can examine atoms and molecules, but we can also examine larger molecules to examine soot formation. We have conventional absorption spectroscopy, so the extinction of light due to absorption, but we also have sophisticated laser spectroscopy, laser-induced fluorescence, Rayleigh measurements, Raman measurement, coherent anti-Stokes-Raman measurement, degenerate four-wave mixing. So there are a lot of nice abbreviation you can find in the literature with specific applications. Here we will focus only on the most important techniques. And at the end, it's not laser diagnostic, but of course it's diagnostic. So I will end with some slides concerning gas chromatography and mass spectrometry. Just some simple, just a simple overview here. So this we have seen yesterday already in a shock tube. You of course can use a pressure sensor to examine the process, and to get your specific signals. If you use several pressures along the pipe, you can measure velocity, and at the end wall, for example, when you reach the T5 zone, after a given delay time, you can measure the ignition delay time. This we can support with emission spectroscopy if we have a proper window applied to our investigation volume. So here we have the emission of OH star, for example, which is then detected by a photomultiplier and stored by a PC recorder. So, and we see here then, okay, the emission also gives us information about the ignition delay time, which is often a better variable to examine your results with numerical calculations. So hopefully today this video will work. So we can perform Schlieren measurements. The idea of Schlieren measurement is when you have density gradients, you have a flow with different densities, and you have density gradients, of course, and you have different volumes with different refractive indexes. So, and when you send light through these volumes at the boundary layer between the two different density volumes, your light is deflected, and what we have here is a typical setup. So we have a light source, we have a typical lens, and then another lens to collect the light. And here we have a knife edge, for example. So the idea is, of course, if the light is not disturbed, we won't see any influence here. But if we have hotter or colder zones, our light is deflected, so it's no longer in line here, and so some part of the light is here moving to the right, and this is then cut out with our night edge. So in our image we would see a darker area, or the other way around, if it's moved in this way, we would see a brighter area. So we see density gradients, and can so visualize shocks, combustion processes. It's also possible to perform quantitative Schlieren measurements. So if you do it very precisely, you can also get information about the temperature field. So here's an example. So we have an early model for diesel combustion. So until in 1984, so it was assumed, okay, we have a jet of a liquid fuel, this vaporize, atomize here, and then we have a diffusion flame here in this area. So this is what they assumed. So here we have the diesel, here we have the air, and the flame takes place here in this area. So then here we perform Schlieren measurements in an optical engine. So we have one cylinder of an engine. Here we have optical access through a small window. Then at the bottom of the piston there is a mirror. We have another window here, and so the light is transmitted to the outside again, and we can collect it with our camera here. So here you can see more in detail the setup. So the light is following this path here, and so we have possibilities to examine our diesel process, and these techniques then have shown finally that the classical model was wrong. So we don't have a classical diffusion flame here outside. So we have a fuel-rich premix reaction zone here. So and combustion take place more or less all over here, and here we have the NOx formation and the soot formation, soot oxidation zone outside. So what is the ideal solution? What would the dream? So it would be nice if we can measure the interesting species, time resolved, and of course radicals, transient intermediates, and even isomers could be detected. And this should be done for all interesting pressures and temperatures. So what can we do already? That's already a lot. Here you see a classical reaction pathway. On the left and on the right you see the soot formation process, starting with simple hydrocarbons plus oxygen. So here we can use absorption, fluorescence, emission, phosphorescence, chemiluminescence, LIF, laser-induced fluorescence, to examine the molecular level. Then we can use LIF for the larger PAH. And finally we have electroluminescence, laser-induced incandescence, and Mie scattering to examine the larger soot molecules. So I will explain all the background here in the following slides. And here, of course, this we have already discussed. We have the possibility to examine our interesting molecules, HO2, H2O2, H, RF, OH, RO2. So we have specific tools here to examine the temporal evolution during elementary reactions, but also during the overall combustion process. Of course, there are limitations. So first of all, we need optical access. That's important. And so for example, one example, if you consider Rayleigh scattering, that means the scattering of our laser light by the molecules in our volume. Laser scattering means the detected wavelength is the same like the excitation wavelengths. The idea is the detected, the scattered light comes only from the molecules along the pathway of the laser. But if we have windows, if we need a closed vessel, we always will have scattering and deflection and so on at the windows, which then of course have big influence to the outcome of our measured scattering light. So it's always important to consider, is the test vessel proper for the measurement method I need to apply. And so what we have discussed yesterday with this shock tube, yes, we can have here optical access. We have quite long observation time, so 2 milliseconds up to 50 milliseconds. However, we have only, in this shock tube, here we have a shock tube, so we have not the possibility of averaging. So we have one shot, and then after 30 minutes we can perform the next experiment. And then of course the question of reproducibility. So even though it may be reproducible with one specific setup, if you then want to compare it with another setup in another lab, there may be deviations we have then of course to consider. But then we can use the whole range of techniques here for this. So we have discussed it shortly also for the flow reactor, where we have access, so we can use laser-based diagnostics also inside a flow reactor. Of course we have to adjust our setup then to have access here, but it's very, very often possible, even though when we have to use closed vessel systems. So the need here is, of course, we need to have a reactor. So our shock tube, RCM or flow reactor, engine, whatever. We need then something we want to examine, and which we can examine using proper laser technique. So LIF, for example, is only possible with selected species. So OH and O, nitric monoxide, can be used easily. CH is also possible, but if we want to, for example, use LIF for H and O atoms, it's getting more and more complicated. Two photon techniques have to be used. So we need for the proper species, first of all, we need a proper species, and then, of course, we need proper light source. Lasers are quite expensive. We are talking about several $100,000 euros for very sophisticated setup. So, of course, this is then the crucial part. You can do whatever you want, but you have to pay for it. So it's quite critical. Then for our elementary reactions, we need normally something like a photolysis source. And of course, finally, we need a detector, photomultipliers or photodiodes, so quite simple. And then we have CCD cameras, and today more and more common are CMOS cameras. They have better detectors, but of course other limits. Again, here on the detector side, we are also talking about money. This is also crucial. So photodiodes, photomultipliers are quite cheap, but if you want to have a very fast CCD camera or have a camera where you can measure high-speed videos, you have to pay for it. So the classical photolysis sources are also lasers. The old fashioned way is to use excimer lasers, but so you have to get them because most of the newer lasers are, for example, neodymium YAG lasers. But of course, you have to consider that you get proper wavelengths to initiate your reaction here. Then, so I will not go too much into details concerning spectroscopy, but at one or two positions we have, of course, have to discuss it. So your molecule is normally in its ground state, so at room temperature, so 300 K. So, and this electronic ground state here is separated in different vibrational states, depending on the temperature. There is a Boltzmann distribution here. And then this vibrational state is, in case of a molecule, of course, then also eventually separated in rotational states. So you have a Boltzmann's distribution of your molecules depending on the temperature you have, and then you can excite them with a laser. So the energy difference is, of course, related to h times nu, the frequency of our laser. So you have to use the proper frequency to match it with the energy difference between the two levels you are interested in. So you excite your molecule to an excited state. Here you have then energy transfer processes. So these excited molecules collide with other molecules. They change their vibrational state, they change their rotational state. And then after a given time, they fall down from a different state, emit some light, fluorescence light, which you then can collect. Or what can happen is that they move to another electronic state. Here it's an excited triplet state. And here they may stay much longer, for a longer time, and then they fall down to the ground state. And so this is then called phosphorescence. So we have different transitions here which we can consider, and always, of course, it depends on our molecule. What is the proper way here? But this is the general assumption. We do not have only scattering from our molecules. There can, of course, be an excitation and so on. Another principle is the absorption spectroscopy, use of Lambert-Berg's law. So we have a light source and send it to our detector, and the intensity of the light behind the detector depends on the length of the cell here, the concentration inside the cell of our molecule of interest, and an extinction coefficient. So, or absorption coefficient. So what we see, if we use proper wavelengths, the light is absorbed depending on the concentration we have. So this is then normally the quantity of interest. Very sophisticated technique, but very common use in chemistry here is the atom resonance absorption spectroscopy. So here we are talking not about molecules, we are talking about the absorption spectroscopy with atoms, and this we can use also with our classical shock tube here. Here we have a specific light source. We have a shutter here, and then we have an solar blind photomultiplier at the end. So we send our light through this volume and probe for specific atoms, depending on the wavelengths we use. So this can be used for a broad range of atoms, and so it based on some work from 1965 where they used a light source for H atoms, and you see 121 nanometers here. We are in the far UV region. It's very high selective due to very high absorption cross section. So you really very, very small amount of H atoms to detect them. So 5 to the power of minus 13 mole per cubic centimeter. This is a very low number here. So we can examine or use it for a lot of reactions, but finally the drawback is we need a calibration. So we have a classical absorbance here as a function of time. But to come from the absorbance to a number of H atoms, we need then of course a calibration curve, and here we see the modeled H atom concentration via absorbance under similar conditions. So this is then always the crucial part. Get your concentration from the measurement. And this has to be done frequently. So if we have different pressures, for example, of course the absorbance is then here influenced too. So this has to be considered. Here we see the absorbance as a function of number of atoms. As some careful background work necessary. So the advantage is we can produce atomic products quite easily. So if we have a hydrocarbon and want to separate H, so it's quite easy to perform. We can examine the consumption in bimolecular reactions. So this reaction in detail I will explain later on, so we can use it for more complex reactions. One disadvantage is we need high purity, so everything produces H atoms, so we have to clean our reactor carefully. Shock tubes need to be very clean and highly electropolished, and we should use only very, very low concentrations because the method is so sensitive. But here an example. So we have CH plus N2 gives HCN plus N. This is the reaction we want to examine here. And so you see we have a quite complex setup. We have a classical shock tube. So driver part to driven part. We use a krypton fluoride laser to initiate the reaction to form our CH radical. We use a laser system to produce laser light at 431 nanometers to measure the CH absorption. And we can use this also to examine the atomic resonance spectroscopy, absorption spectroscopy for N atoms. Of course, we need a proper mixing system, but the sophisticated part is here to have a proper timing. Okay, here we have a continuous wave laser system. That's maybe not a big problem, but we need to trigger this laser, eventually this laser, the camera system, based on specific timing. So we need to know exactly when our shocks are at this position, and we need to know exactly, okay, is there a delay between trigger signal and the laser pulse here and the laser pulse here, the gating of our camera. So it's quite complex if you use multiple techniques. And this is just for one single reaction. So here you see a sketch of a flow reactor, and here we initiate the photolysis with UV lamp absorption. So we have seen this image before. So we have a flow reactor, so the flow is moving through in this way through our reactor, and here we have optical windows to examine the flow before and after the reaction volume we have here. So here we use a laser again, an argon fluoride excimer laser, to initiate the reaction of interest in our flow reactor, and we use then an HD xenon high pressure lamp to produce ultraviolet light and in the visible range. and then we measure the absorption of the light inside our reactor, and here the absorption is mainly from HO2. So here we have a premixed NH3O2 mixture in our reactor, flow reactor, and finally we measure then the HO2 concentration to get some information about the reaction of interest. So, example here, we have the HO2 as a function of time signal. So we see that it increases when the flow enters our flow reactor, and so the reaction initiated, and finally the saturation level is reached here. So of course, this technique, which is quite simple, has disadvantages. First of all, many species can absorb here a light, can have an absorption cross-section in this specific region. So advantages, you can use it for every species, nearly every species. However, if you have several of them in your reactor, it's quite difficult to separate them, so the spectral overlap is the disadvantages. And what we do today normally is TD-LAS technique. So we have specific lasers we use. So we have only very small wavelengths, which we send to our test vessel. So tunable diode lasers are used here. They are very cheap because they are used for telecommunication in our days, and the advantage is that we can use it for a lot of different wavelengths. So we can use for each molecule one specific laser with a very narrow wavelengths. So the spectral overlap problem can be avoided then, of course, because we can examine the absorption by different molecules within one experiment. So then, of course, you have to consider something like temperature dependency, pressure dependency. I said in the beginning, the absorption depends on the concentration of our molecule. But also, this, of course, is then related to temperature and pressure. So here for this CH3O2 example, it's visible how the cross section decays with temperature. So you need to know precisely how this change for a precise measurement. So here's an example, a quite easy example. So the absorption cross section for hydrogen peroxide as a function of wavelengths. This you have to consider. Here it's for HO2 as a function of wavelengths at room temperature. So you need to know a lot of details if you want to perform your measurement really precisely. And here you see it can be quite complex. So here we have the temperature dependency for toluene, which looks quite confusing. We do not longer have an single linear relation of our signal. So when you change the temperature, you can see how the shape of this absorption cross section as a function of wavelengths change with temperature change. So and finally, Of course, you can use these techniques combined. So we have discussed this already very shortly. So here we have an reactor where we initiate the reaction with a neodymium laser. Then we can use a 308 nanometer for laser-induced fluorescence and a laser to examine the OH radical. And here for HO2, we use a diode laser for the absorption measurements. So we can probe within one reactor several molecules to get more information about the reaction. Continue with cavity ring-down spectroscopy. So here we use a YAG laser and a so-called optical parametric oscillator, an OPO, which then produces the final wavelengths of interest. And this we then can send into our cavity here. And the main idea is here we have highly reflective mirrors here. So our light is then reflected very often within our cavity. And we measure finally with a photodiode the intensity of the light which comes out of the vessel. So the idea is here our light enters, and depending on the gas mixture inside the cavity, there can be, first of all, there has to be a molecule which can absorb this frequency. And if it's there, you can see that the light hitting our detector, of course, decays as a function of time. So with each reflection, or after each reflection, the intensity decreases because it's absorbed, or some amount of the light is absorbed by the molecules. So we get this graph finally, so an exponential decay of our laser light, and so we can use this technique to measure very, very small concentration. So it's a very high sensitive method. It's not dependent on the initial laser intensity. So shot-to-shot variation concerning the energy of our laser has no influence here. So we can repeat the measurement quite often. So we can maybe even after several milliseconds we can perform the next shot. So it has a lot of disadvantages, but so first of all we need a proper light source, a proper laser here. This is today no longer the big issue. We need proper mirrors here for this specific wavelengths. But finally the main problem is it's quite expensive. So we need a laser, of course, and we need proper mirrors here, which together is quite expensive compared to other techniques. So laser-induced fluorescence. This is typical workhorse for combustion experiments. Here we have a more simple setup. So we have our ground level. Our molecules are normally here in this ground level of the this electronic state here. Even at combustion conditions, then depending on the temperature, they may be in different vibrational or rotational states. So we can use in classical Boltzmann distribution here to get information. So how many OH atom we assume in which energy level. And then we can use a laser with a proper frequency to excite molecules from the ground state to the upper state. Then here we have energy transition in the upper state. And finally, after a specific time, this molecule falls down to the ground state and emits light with a frequency depending on the energy gap between the specific level here and the specific level there. So we excite our electron inside our molecule from one specific energy level to a higher energy level, and after a given time it falls down, we can detect the fluorescence. So again, we have to take care. So this is a very narrow band laser normally. We can also use broadband lasers, but normally this is a narrow band laser. So this has one specific frequency. However, the emission spectra consists a lot of lines or even bands. So we have a broad detection region here, and it's quite difficult, for example, to perform quantitative analysis here due to the processes leading to the distribution of our molecules in the upper electronic state. So when we go a little bit more into details, here we see the electronic ground state. We see here different vibrational levels. V equals 0, V equals 1. And inside these vibrational levels, we see different rotational levels. So the population here depends, of course, then on the Boltzmann distribution. We excite from one specific rotational level in one specific vibrational level in the electronic ground state to this upper electronical state. We reach one specific level. This depends on the laser wavelengths we use. But then, of course, we have a distribution here due to collision processes and other processes. We can have pre-dissociation and so on. It depends really on the system we examine, what is happening here in the upper level before finally the electron falls down. So, and even though if they come from one level here, they can fall down into several levels here. So only this leads to different frequencies in our emission spectra. So it can be quite complex. But we can use this technique, for example, here in our flow reactor. Again, we use a krypton fluoride laser to initiate the reaction of interest. And then here we use an neodymium laser to examine OH live. So this is one specific transition we excite here to have access here. That's the advantage. Neodymium laser plus dye lasers are quite cheap, and this detection wavelengths is quite common in our days, or this excitation wavelengths, sorry. So how does it look like? We have our high pressure cell. We use this excimer laser for excitation or the initiation of the reaction. Here we have our YAG laser dye laser system to produce the light at 281 nanometers. We send this to our cell, and in this example we have quite a simple photomultiplier which then collects our fluorescence light. which is then selected 90 degrees or perpendicular to our normal to our laser beam. So then for this setup, we examine OH, and we can see, for example, the intensity of the fluorescence light as a function of time. So here for two different temperatures and pressures. And this then can be used to examine in detail, for example, here, elementary reactions. More popular, maybe more insight can be yielded using planar laser-induced fluorescence when we consider combustion processes. So we have a laser source, and then we use a laser system to produce a laser sheet. So it has a given height up to several centimeters, and it's normally very small, so in a range of 100-200 micrometers. So we have a sheet which we send to our probe volume, our flame, for example, our combustion cell, and then 90 degrees or in a specific angle to our laser, we have a camera where we can detect the emitted fluorescence light. And normally we use a filter here to get rid of the scattered initial wavelengths of the laser source. So finally we get information about the fluorescence as a function of the position inside the flame. So here an example. So this is a photography of the flame at different equivalence ratio. We see here quite blue flame, mainly only CH we can see here. Then you see how the structure and the color changes. So on the right hand side we have a yellow flame again. So a lot of soot formation eventually. And so we can measure, for example, the temperature, in this case using so-called two-line thermometry. So we have the temperature here, signal strength, and so on. And so how does it work? We use two lasers with two specific wavelengths. Maybe I go back here. So we excite two selected ground states here to two selected rotational levels in the lowest vibrational level, normally in the electronic ground state. And so we have a Boltzmann distribution, this we know. So if we know the initial temperature, so we know how many, or we want to know the temperature, and therefore when we measure the intensity at one specific wavelength and a second specific wavelength, we get information about the Boltzmann distribution in the ground state. And this then finally gives us information about the temperature in inside the molecule or inside the combustion chamber. But again, you see we need two laser systems, so two YAG lasers, two dye lasers, quite expensive system together with two ICCDs. So then we can come to laser induced incandescence. This we use for examination of soot formation. So we have particles in our flame, for example, here, and we heat these particles up with a laser, to a specific temperature, they start to glow, and this glow light then can be detected. And we can yield several information about these particles from this emitted light. So we can measure first of all soot volume fraction. We can get information about the particle size. So we can perform planar measurements. We can perform temporal resolved measurements. Of course, there are limitations. There should not be too much soot, otherwise we will face some problems. We need high power lasers, so quite expensive again. We need proper detectors with short gating time. And of course, we have to consider, are there other excitations? For example, if we have classical hydrocarbon flame, or here with precursors like benzene, there will also be broadband fluorescence. So we have, in addition to the light from the incandescence, we also have fluorescence light, and this we may use proper filters or proper detection system to separate this. So the typical application is examination of soot growth and destruction in laminar flames, or soot emission, for example, from diesel engines. So the idea is, so we heat up our soot particle, and then we detect the thermal radiation as a function of time, for example. And but what we have to consider is, of course, when we heat up this particle, we have some vaporization, we have heat conduction, we have thermal radiation. This then, of course, finally influences the temperature of our molecule. But if we do it properly, we can calculate the temporal profile of our incandescence as a function of temperature. So here, the only mathematical details for today. So we heat up our particle, and so we want to measure the radiation, which is the function of temperature, of course. And we have to consider vaporization, we have to consider heat transfer. So it's possible, or it's necessary, to have an accurate description of the heat mass transport kinetics if we want to get the proper outcome here. But it can be used also in quite complex geometries. Here it's again an optical accessible engine, where we use a laser sheet here to heat up our particles, and we can use a mirror here to measure the emitted light. So we get information, for example, about the growth of the soot particles, the position of the particles inside our diesel fuel here, diesel combustion process. We can, when we combine it with, for example, laser-induced fluorescence from the PAH, we can see the area where we have soot. So inside here we see the precursors leading to soot, but the soot signal we can see only here at the outer, in the outer region. So this is a classical image here for a burner. So the reaction starts somewhere here, and finally we come to the soot region, and so we can use a laser sheet somewhere here or a laser beam, and then we get a radial intensity profile at a function of height, for example. So we can get qualified information about the amount of soot here together again with the fluorescence of PAH to examine the soot formation process in detail. This we can also mix with Rayleigh scattering, so-called Rayleighs. So you can see now the setup is already getting quite complex. First of all, we have again a neodymium YAG laser here. So and then we produce a train of laser sheets here to use the whole energy range of our lasers. So we extend the temporal length of the laser, increase the energy per time, but the total amount of energy stays the same. And so we can then examine the incandescence with one camera and the scattered light with another camera, with using proper filter systems. So we get several information within one experiment. Here we can use this for temporal resolution. So it's a quite fast process. So we are talking about nanoseconds up to microseconds. We need between several consecutive experiments. So this is a typical outcome. So we have one signal so measured here at different height above the burner, and you see a comparison with the calculated signal, so it's quite good. So we have we yield very precise information here using this technique. So I continue with gas chromatography and mass spectrometry as a final part for today. So we won't have a break, but I think maybe we need a maximum 30 more minutes, plus the questions discussion afterwards. So most of the this lecture you have survived already. So the rest is maybe also handleable. So gas chromatography, so or mass spectrometry. So we leave now laser diagnostics. We have here two techniques to separate gas mixtures using different methods. So we get information about which species we have. So the molecule of interest, and we also can get quantitative information. So how much of each molecule we have. Of course, it has some disadvantages. So we have to catch our probe, and if we, for example, want to extract some molecules from our gas phase and send it to a gas chromatograph, it will cool down. Some reactions will continue, so the mixture at the end of the gas chromatograph is maybe not the same we have extracted from our gas, our flame, and we don't have any time resolved information directly, so we have to repeat the measurement very often at different times, for example. So the idea is quite simple. We have a sample injector, we have a column here with a carrier gas, and at the end we have a detector. So we have something like a so-called retention time. So within this column, the different molecules we inject need different times until they reach the detector. So simply speaking, the lighter molecules are faster here than the heavier ones, but of course it depends on our column we use. But nevertheless, at the end, we want to separate our molecules using this column. And this can be done for also complex systems. Here we again have a shock tube. Here we have a sample port in our region of interest. And here we use two different columns, one for lighter hydrocarbons, one for heavier hydrocarbons. So we get quite sophisticated information here. And here this is then coupled to flame ionization detectors. So we can then not only separate the molecules by the GC, using this FID we can also determine the amount of molecules we have. So we have quantitative information about how much molecules we have and what different molecules we have. So it's quite a helpful method. And this is one of the advantages if we have a proper reactor. This can be automatic. So this can be done several times in repetition. And we yield a lot of information here. Of course, this depends then on our reactor. So here the principle of this flame ionization detector can be seen. So we have the column with our molecules. We have hydrogen here to have a stable flame here. And then when our probe molecules enter this flame, we can measure the ionization inside this flame. So we have an electric field here, and depending on the combustible, depending on the molecules we have here in this flame, we see a different response of the ions here in this flame, and so we can then finally collect or get information about what molecules we have in what quantity. So what we get from the column and the intensity here then of the response of the amount of ionization gives us information how much molecules we have. Okay, this I skip. So when we look at in classical GC, you can see here intensity, for example. So we can separate a lot of different molecules here, again as a function of time. So it depends, of course, on our column, which molecules come first. But here we have some bigger hydrocarbons separated. Here we see only the mass of the different molecules. So it's quite interesting. So mass spectrometry as a last technique we want to discuss today is of course more complex, but gives us more detailed information about the mass of our species inside our reactor. So the idea is here we have a reactor, our reaction takes place here, and we suck out some probe volume out of the reactor, put it into our mass spectrometer, and so then we ionize our molecules here, and depending on the mass of the species we have, so these ionized molecules have to flow through an electrical field, and then of course they will be, depending on their mass, they will be detected at different positions. So we have a 2D time and position sensitive detector, and then can separate the molecules by their mass. So it's quite easy, but of course we have to consider, so we suck out some molecules here, and we need some time until they reach the detector. However, the advantage is we have nearly vacuum here inside this cell. So the probability that the excited or the intermediate species will collide again, further reaction will take place, is quite low. If we use a proper setup here, we can really get the information we want about the reaction of interest. So here's an example. So they used the advanced light source in Berkeley, combined with this mass spectrometry. So even very sophisticated measurements are possible to for a simultaneous detection of multiple masses under engine relevant conditions. It's a very, very helpful technique to get detailed information here. So we get additional information when we then consider also the time of flight. So how long need these molecules until they reach their final destination. So you can see here, if we use a linear time of flight mass spectrometer, we cannot resolve this broad peak here, but if we have a modification, so-called reflection time of flight, you can see here 3 or 4 different peaks. They even have a fifth one here. So and the difference is just 1 Dalton here, so 1347 and 1348. So it has a very high resolution on these techniques. So I'll come to an end, with the last topic, flow visualization, particle image velocimetry. This can be used to examine the flow field. So we add normally particles, either solid particles or liquid particles, to our flow, and we have use a laser system to follow these particles. That means we have a laser sheet, then we have scattering from our particles, and after a given time we send a second laser pulse to the same system, and our particles have moved depending on the flow field, and so we get two consecutive images of our flow field with a given time distance, and using some mathematical methods, we then finally can follow the different particles in the flow field, and for each volume we can then calculate the velocity of the particles, and normally the assumption is correct that the velocity of the flow field is equal to the velocity of the particles. So we get then information about the flow field in detail, and it's the advantage, it's a quite simple technique, and we have an 2D configuration. Here you see the vectors of the flow field, and here it was combined with an OH measurement. So we have we see here more or less combustion taking place. So this is then of course necessary if we want to examine the interaction of the flow field with our flame, or like Professor Sahu has said in the morning, there can be extinction, for example, if we have too much strain, so the flow field is too intensive. So this can be examined, for example, with combination of PIV and OH LIF. Here this is done for a swirling flame, so the flow is coming from the bottom, and then here we see the flow field of our flame. So the technique is quite simple. First of all, you need a proper laser, or laser system, either two single lasers or one laser which is capable to be operated in a double pulse option, that you get two laser beams in a given time distance of microseconds normally, and each laser pulse should have a very short pulse duration. So it's quite easy. So you get scattering. You may see the white particles here. It's very sensitive technique. And then the problem is you get two of these images. You have maybe thousands of particles on your image at one given time, and the second image a little bit later, and then to correlate the change of position of each particle. But here this is nowadays standard, so normally you have proper software, and this is done more or less automatically. But of course you have to double check here, is everything correct? But with two images you can get quite simple information about the flow field. So that's for today. Do you have any questions?
Sir, UV lamp absorption techniques.
Mhm.
Can it be used for all kind of reactions?
First of all, you need a molecule which absorbs. So then this has to be considered. In principle, yes, but the correct answer, it depends.
So it depends on the species we are going to detect, and for that we need to use different kind of lasers.
Yeah, so the modern application is using these TDLS lasers. So the modern communication lasers we have at several wavelengths. So we can use it for specific molecules, so ammonia, hydrogen, NO, and so on. Mainly water. So that's the typical application.
And the YAZ laser, you say it's used for what purpose?
Pardon?
YAZ, YAG laser.
Yeah.
So for what purpose it is being used?
So there exist several so-called solid-state lasers. Neodymium YAG is just one possible um, um, realization here. There are others, deuterium lasers and so on. So you find different solid-state lasers. The advantages, they are quite cheap and quite reliable in our days. So these excimer lasers, which I have shown here, were more popular in the past. And nowadays we use more these solid-state lasers. And neodymium YAG laser produces light at 1064 nanometers. So that's the fundamental line, and this can be then frequency doubled to 432 nanometers. And for OH, for example, we use then a dye laser with rhodamine 6G. So we yield then, when we use this 432 nanometers of a dye laser, we yield after the dye laser process 560 nanometer. This is then again frequency doubled, and we get light at 280 nanometers, which we then use for OH. Yeah, so another application is you can frequency triple your neodymium YAG laser, and you get light at 355 nanometers, which can be used for other dye laser excitations. For example, when you want to go to NO fluorescence, you need 226 at the end. So using coumarine in your dye laser, get 450, frequency double 225. Or use it directly for hydrocarbon flames. Maybe you can see so CH already with 355, and you can quadruple this laser light 266 nanometers. So you have 4 different fundamentals which you can use for different applications, and you have really high energy lasers in our days already, so range of joules per pulse. So I have shown you on one image how they separate this laser, this very short laser pulse, and so they lengthen it so to decrease the amount of energy per time. But then you can couple a very high energy into your probe volume for example, Raman measurements, Rayleigh measurements. So it's for me, this is a typical workhorse in our days, the neodymium YAG laser.
And for the same purpose, I hope we are also using krypton chloride laser here.
Pardon?
Krypton chloride laser.
Yeah.
It's also used for the same reason for OH detection.
Yeah, it's so the 00 band of OH is at 208 nanometers, and then 10 is 281. So where we use this normally this near the MIAC dye laser system, and at 2488 we can use predissociation LIF. So there's a 3-0 band. So we can also use 248 nanometers to examine OH radicals.
And when you are using this laser-based diagnosis system, whether it is LIF, PLIF, are you getting any kind of quantitative analysis out of that? For example, when you are using GCMS, you said we are getting quantitative and qualitative analysis.
Yeah.
Is the same thing happened with laser-induced fluorescence, LIF or PLIF?
This is a difficult question. You can, it depends on the molecule, first of all. For example, for OH is quite difficult because you have a lot of energy transfer processes. So, as I said, you excite with one specific wavelength, but you get an excitation emission spectrum which is very broad. So, because you have energy transfer processes in the upper electronic ground state, so you are excited, OH molecules collide with water, collide with nitrogen, collide with other molecules, and each collision changes the electronic, the energy level of this OH, and when then the OH molecules fall down to the ground state, they fall down to different levels in the ground state. So you have a lot of lines you see, and so you see, so you excite, for example, at 281 point, maybe 2 digits after the comma, very precisely, and then you get light in the range from 210 to 270 nanometers, 310 to 270 nanometers, and so the intensity of your fluorescence light does not depend only on the amount of OH you have, but also on the energy transfer due to collision and so on. So this is quite difficult. So for OH, normally you see only qualitative results.
TIGLAS is available for all the species?
No, this is then mainly the work of Ravi, who spent a lot of money to find proper lasers for proper wavelengths. Yeah, so as I said, these are mainly telecommunication lasers. So you get more and more wavelengths here, but of course not for every specific wavelength.
Another thing is that while measuring in TIGLAS, so is it the ray of the laser or it is converted to a seed?
Pardon?
The laser is applied as a ray, means a straight line, or
Yeah.
it is converted to seed?
No, this is a line of sight technique. So you measure the absorption, and so you send a small line, you send just a line through your vessel, and then you measure the absorption along the length of your cell.
How to ensure that the mixture is homogeneous after the combustion process, so that a line only gives you the best result, not a seed? I think a seed can give you the average value of that one, or a volumetric analysis can give the better value.
You mean so the application of this TD-Last technique for combustion processes? Yeah, yeah, that's the critical thing here. You have to have homogeneous conditions along the length or the way of your laser beam. So when you want to get quantitative information. So you're absolutely right. If you look into a flame cone where you have a change of composition, then you see only quantitatively is there absorption, how much absorption there is, but you cannot resolve it in a way that to say, okay, I have this amount of absorber here. No? So the crucial criteria for a quantitative measurement is that you have a homogeneous mixture at known temperature and pressure.
So, sir, this LIF or PLIF compared to GCMS, will there be any change in result or variation in result if you are collecting the sample and using it in GCMS rather than going for LIF or PLIF?
First of all, it's so LIF is mainly used for the smaller molecules. Now, okay, we can use it for the big hydrocarbons too, but if you are interested in the reaction zone, you mainly use it for the smaller molecules, OH and so on. While GC-MS gives more information about the more stable molecules you have, the larger molecules. When you compare it then maybe with mass spectrometry, where we also can measure the smaller particles, we always have to consider that laser-induced fluorescence is an instantaneous measurement. We look directly at the position where the chemistry takes place.
But here we are collecting it and then...
Yeah, and then there maybe is a change of mixture composition. Some follow-up reaction can take place and so on. So this always has to be considered. Therefore, it's difficult to say which one is better. We need both of them.
Normally you used to collect the sample and then go to GC and MS and test it.
Yeah. So gas chromatography, I would recommend if you have stable molecules, which do not react along the column. It takes a long time until they reach, for example, the flame ionization detector. First of all, you separate them by mass, and then you check how much you have at which mass. So this is very precise. So you can go down to parts per billion. This is very, very precise. However, if you take it from a flame, what you measure at the end is maybe not identical to what you have sucked out of the flame. So here an MS is much better because you have a vacuum behind your nozzle, so most of the reactions no longer take place because the probability of collision is quite low. Okay, so thank you very much.
Yeah.